Okay, I see that it's now, according to my clock at least, 1 minute after 1, so I think we should get started. My name is Michelle Dunn. I am in the Office of the Associate Director for Data Science, and it is my great pleasure to introduce today's Frontiers lecture. We have not one but two speakers today. The first one, and as advertised, is Anthony Goldbloom. Anthony is the founder and CEO of Kaggle. Kaggle, as you probably know, is a Silicon Valley startup that hosts predictive modeling competitions. Anthony has had a great number of honors bestowed on him, including from popular press, such as Forbes magazine, who named him one of the 30 under 30 in technology. Anthony comes from Melbourne, Australia, and with a background in economics and econometrics, but more recently and currently lives in California. So he's joining us via WebEx from California. And in addition, a bit closer to home, we have Dr. Andrew Arai joining us, who is a PI, a tenured investigator at the National Heart, Lung, and Blood Institute. He's been at NIH since 1993, and he has had a very productive career here at NIH, including getting a PCASE award early on in his career. He is now actively involved in developing new imaging methods, and in particular MRI technologies that can be used in the clinic. Dr. Arai will tell us about some work that he has done with Anthony after Anthony starts off with talking about some of the things that Google has done. But before I turn it over to Anthony, I want to say a couple of housekeeping things. The first is that we are being recorded, and this lecture will be archived online. The second is, if you haven't already done so, or if you weren't automatically muted when you came in, please do mute. And the third is that we're going to have plenty of time for questions. I know that Anthony plans on stopping during his talk in case there are questions. Feel free to ask then, or save your questions till the end. We will have plenty of time for that. And then finally, if you are looking at the splash slide right now that has Anthony's picture on it, you should go up to the top of your WebEx and click on the tab that says Anthony Goldbloom, or depending on how long your tab is, Anthony or Anthony Goldbloom, to get over to his slides. So at this point, I'd like to turn it over to Anthony. And Anthony, thank you so much for joining us.
Thanks very much. Thanks, Michelle. Yeah, thank you very much for hosting. So I'm going to do a couple of things. I'm first of all going to talk about how data science and machine learning competitions work and how Kaggle works. Then I'm going to go over in not very much detail a bit of a summary of some of our case studies in healthcare, and then I'm going to turn over to Andrew Arai, who's going to do a much deeper dive into into one particular case study. It's a competition that we finished very recently. The NIH was a major collaborator in that competition, and so I thought it might be interesting, to do a deeper dive and a deeper case study. So to start off, for those of you who aren't familiar with Kaggle or machine learning competitions, how they work is we'll post a problem, and any data scientist or statistician from anywhere in the world can elect to participate in one of our competitions. So these competitions really range. They range from public sector to private sector. They range from medical imaging related problems, such as the one that Dr. Arai is going to talk about in more detail, taking MRIs to diagnose heart failure. We've worked with Genentech to predict at-risk populations for cervical cancer. We've worked with the Allen Institute for Artificial Intelligence on can you build an algorithm to solve an 8th grade science quiz. Stock market predictions, an obvious use case. We've worked with Home Depot on improving their search algorithm. So when you search for a certain power tool, getting back a result that is more accurate. and Prudential on life insurance assessment. I'm giving you these examples more just to give you a sense for the breadth of what machine learning and data science can be applied to. So it really is what Andrew McAfee and Eric Brynjolfsson of MIT call a general purpose technology, one that can be applied in so many different areas. Now, the structure, you'll notice on the right-hand side, we have a certain number of teams, we have a certain amount of prize money, and so teams will, the winning team will win prize money. In exchange, they'll give the algorithm over to the organization or the company that sponsors the competition. Now, the structure of competitions is really very simple. We give out, this is an indicative, no problem is really as simple as this, but I show this example to give you a sense for what the competitions look like. It probably seems like it's black magic, but it's actually quite simple. We give out two data sets. We give out what's called a training data set, so you can take age and income, and you're trying to predict default. And then we give out a test data set, so age and income. We know who defaulted, but we withhold that information. And so we give out both data sets. Now, what a data scientist will do is they'll train their algorithm on this first data set, the training data set, and then they'll apply their algorithms on this data set, the test data set. Now, in both cases, these are past, in this case, it's helping a bank predict who's going to default on a loan. In both cases, they're past borrowers, so we know who defaulted, and so we're able to score objectively people's performance against this test data set where we know the answers, but nobody else has access to the answers. And the idea here is once you have trained an algorithm that works well on historical data, you can then apply it in the future to make future, in this case, it's loan decisions. In the case of the case study that Dr. Arai is going to talk about, it's medical diagnosis decisions. If you train on past medical diagnoses, then you can apply the same algorithm to the future to make medical diagnoses in the future. I'm going to pause there to ask if anyone has any questions, because I know this part is, once you understand this part, I think the rest of it is relatively straightforward. So are there any questions? Please unmute and ask your question if you have one. I can't see the text chat, so I won't see text questions. No, okay, I will keep going. Please, if you do have a question, you feel free to interrupt. I know it takes a minute to unmute. So because we have this test data set, we can objectively judge how people are performing. So this is the live leaderboard, and you can see here the first place team has a score of 0.56, and they've made 86 entries. Now, typical competition, depending on this complexity, will last for between 2 and 4 months. And so each day, a data scientist can come back and they can put up to 5 entries. And so on day 1, you get a certain score and you see how you're performing relative to others. And then the next day, you come back and you try and improve that score. And the next day, you try and improve that score. And we show that people's scores in real time for a few reasons, but the main one being that it ends up being a big motivator. So if you're working on a problem in isolation, you don't know how well you're doing. You don't know whether whether there might be more you can get out of the data set. When you see how you're performing relative to others, that motivates you to put in more effort if you're a little bit off the pace. So it's a very, very powerful dynamic and an important part of Kaggle. One thing I should say, this is important, is we show people how they're performing on a live leaderboard, but before we award the prize money, we retest them on a second test data set. So I showed you this simple structure. In reality, there is 1 training set and there are 2 test data sets. Now, really what we're worried about is we want to protect against a statistical concept called overfitting. And what overfitting is it's a situation where you build an algorithm that performs very well on 1 test data set but doesn't generalize well. And so people get a sense for how they're performing on the live leaderboard, but before we actually award the prize money, we retest them on a second test data set to make sure their algorithm continues to perform well on a test data set where they've received no feedback. Now, I mentioned to you that the leaderboards are a very powerful motivator. Now, I'm going to illustrate this concept with one of our very early competitions. Now, this was a competition that we did with NASA, and what they wanted to do was they wanted to take images of galaxies, and they wanted to measure very precisely the ellipticity of those galaxies. And so they provided lots of galaxy images. They provided ellipticities, and data scientists had to build an algorithm that sort of measured very precisely from the images they were taking, the telescope images, what the actual ellipticity of the galaxy was. Now, the first person to make a breakthrough on this problem was a guy called Martin O'Leary. Now, Martin was a PhD student at the time at Cambridge University, and he was a PhD student in glaciology. Now, I had never heard of glaciology before Martin, but apparently what Martin would do in his research is he would take satellite images of glaciers and detect algorithmically where the edges of the glaciers were. So if you think about it like this, a telescope is looking down at the Earth and he's doing edge detection, and so the algorithms that he had developed for his glaciology research actually were quite a good fit for taking telescope images and measuring the ellipticity of galaxies. And so it turned out that he had a technique that was very powerful and was actually quite a big breakthrough for NASA. Now, I have a chart up here. The way to understand this chart is the y-axis is error, the lower the better, the x-axis is time. And so Martin made a first entry and he got, or an early entry, and got to first place on the leaderboard. Now, NASA were very pleased with this result because Martin had basically outperformed what the accuracy of the algorithms that they had developed previously. And so Jason Rhodes, who was the investigator at NASA, who was behind this competition, posted a blog post on the White House Office of Science and Technology Policy blog, where he said the world's brightest physicists have been working on this problem for many decades, or it's one of the great unifying problems of our universe. They've been working on it for a while. In less than a week, Martin O'Leary, this PhD student, had made a really nice breakthrough. Now, Martin has a sense of humor and he has a Twitter account, and so I should point this out before I give you this fun anecdote, but in the post, Jason refers to Einstein's theory of relativity and Newton's law of gravity, so sort of explaining the significance of this problem. If you can measure the ellipticity of galaxies very accurately, then depending on how much dark matter there is between the observer and the galaxy, it'll tell you whether or not the galaxy is being gravitationally lensed. So you can back out from these ellipticity measurements what the dark matter distribution of the universe is. So it's quite an important problem. So, Jason references the background behind dark matter and Einstein's theory of relativity and Newton's law of gravity. And Martin, who has, as I said, both a Twitter account and a sense of humor, got on Twitter and he said, not that I'm bragging or nothing, but the White House has just compared me to Einstein and Newton. So he was very pleased with himself. But he doesn't remain pleased for very long, because what happens is then somebody passes him. As you can see in the leaderboard, Martin was in first place, now somebody's passed him. And you can predict what happens next. So Martin might have stopped previously with the performance he had, but now we know it's possible to do better. So then Martin gets ahead of them, and they get ahead of him, and he gets ahead of them. And eventually you get to this point where nobody is actually improving at all on the performance of the algorithm. Now, how to understand this is, in a data set, there is a signal and there's noise. So very rare the situations where you can predict with 100% accuracy. There's normally, there's anomalies. If it's medical imaging, maybe the scanner didn't work very well. Maybe somebody is presenting with a symptom that you've never seen before. You can very rarely predict with 100% accuracy. And so what is typically the case is, given the state of the art in data science and machine learning, and given that the data set you have, it's typically only possible to ever get a certain level of accuracy. And competitions end up being a very, very powerful way to get to that limit. So for whatever signal there is in a data set, if you're a single investigator trying the methods without the motivation of a competition, you get the best you can possibly get, whereas, or the best you can get sort of given the circumstances under which you're working. And it's very rarely the case that that's the limit of what you can get out of the data set. And so this competitive situation pushes people to score better than they otherwise would. If you think about it from companies' perspectives or organizations' perspectives, why do they host competitions on Kaggle? Well, they host competitions really for two reasons. One is they have an existing algorithm. They have no idea how it's performing relative to its potential. It's possible that it's performing at this level and they could be doing a lot better. It's possible it's performing right at that frontier already, and there's no way to know. So at the end of a competition, a company or an organization gets a researcher gets sort of a clear sense for what is possible at the cutting edge of machine learning given my data set. So it's a very good way to get that answer. So go on. I think there's a question. Is there a question? I'll keep going, but if there is a question. Sorry, go on. Hello. All right, I will keep going. If that question does come back, yell it out, or if it gets mentioned on text chat, if somebody else could repeat the question. So the other reason that researchers, companies, organizations use competitions is it's a very quick way to not draw a false negative on a certain conclusion, on a certain algorithm. So, you know, sometimes a company or a researcher is trying something very difficult, and there is a risk that you draw a false negative, that maybe the set of techniques that were tried weren't the right set of techniques, and so you know, trying to do whatever it was that the investigator was trying to do turned out to be or it looked like it was not possible when actually it was, if a different set of techniques might have been used. So that's why companies and researchers typically put problems up on Kaggle. On the flip side, why do people participate? So we have a community now of 530,000 data scientists. So it's really hard to know how many data scientists there are in the world. The number I've heard quoted, and this is not a very robust number, I've heard people say there are about 2 million data scientists in the world. And so at least given that rule of thumb, we have about a little bit more than a quarter of the world's data science population competing on Kaggle. Now, the reason they compete is for a variety of reasons. The first reason, the number one reason is to learn. So you come to Kaggle, you get exposed to lots of different problems. You know, maybe you finished 300th or even 3,000. Some of our competitions get up to 5,000 teams enter. And at the end of the competition, you not only know what you did and how you performed, but you typically the winners will talk a little bit about some of the techniques that they use. So it gives a data scientist who wants to improve themselves, both they've worked on a problem, but then they see what other people did on that problem. And it turns out to be a very, very, very efficient way to learn. So that's the number one motivation. Probably close behind learning as a motivation is a credential. So data science, the best definition I've heard is that data science is more programming than a statistician and more statistics than a programmer. And now that requires people to be self-taught in one of those two fields. You're either, because not many people have a formal training in both. And so it's very difficult to demonstrate on a CV that you're a strong data scientist. And so data scientists compete on Kaggle in order to be able to put on their CVs. You'll see, if you screen data science CVs, you see a lot of CVs show people's performance in Kaggle competitions. It's become a de facto credential in the data science world, in the absence of, you know, there haven't until recently been university courses. There haven't really been, no one has sort of a significant amount of experience in the combination of disciplines required to be able to be badged a data scientist. And so we fill that credentialing gap. And then the third reason is we get a lot of usage from machine learning researchers. So these are PhDs, postdocs, tenured academics who compete on Kaggle really to, when they have a new technique, you can publish in a paper, and then 4 years later it starts to get a critical mass of citations, and then several years later it sort of starts to make its way into some of the bleeding edge companies like Google and Facebook, and then it ends up over a longer period of time, it becomes the standard. If you win a competition using a new technique, all of a sudden all the people you beat are paying very close attention to what you did. And so we've seen a lot of techniques pioneered through, or not pioneered, but spread through Kaggle. Geoffrey Hinton at the University of Toronto first won a competition using deep neural networks or deep learning in 2012. One of his grad students won the next competition using deep neural networks or deep learning. And so all of a sudden there was a lot of interest in deep learning within the Kaggle community, which, as I said, is a non-trivial proportion of the data science universe, and so it ends up being a very good way to propagate new techniques. Most recently, a new algorithm called XGBoost, which is for those of you who are machine learning, have a machine learning background, it's a nice implementation of gradient boosting machines. So again, Tianqi Chen used Kaggle to sort of demonstrate that XGBoost was a very powerful new technique. So that's why people participate. Just to give you a sense for the amount of activity, we're consistently at the moment hitting over 100,000 submissions, machine learning models submitted to Kaggle competitions each month. So there's a huge amount of hours spent on these competitions. Just to give you a sense, a typical submission will take about 5 hours of somebody's time to put together. So it's a large number of hours being spent on our competitions. So I'm going to go through a couple of case studies now that are healthcare-oriented. I'm going to go through these in relatively brief detail because Dr. Arai is going to go through the MRI to measure heart failure or ejection fraction one in more detail. So medical imaging has become a really interesting area for us, and an area where we're seeing a huge amount of potential. And this is as a result of a new technique called deep learning, and more specifically a branch of deep learning called convolutional neural networks. Our first medical imaging success was last year, was with UC Berkeley and the California Healthcare Foundation, and it was taking images of the eye and diagnosing an eye disease called diabetic retinopathy. Now, just to give a bit of background on at least my understanding of diabetic retinopathy, so it's a side effect of not well-managed diabetes. If you suffer from diabetic retinopathy, you end up blind, and so if you have a rating of 0, you have no diabetic retinopathy, and that's the eye you see in the top left-hand corner. If you have a rating of 1 or 2, you have mild diabetic retinopathy. At that point, it's treatable. So you can have laser surgery, or you can have an injection, and either of those treatments will prevent blindness. As you get to level 3 and level 4, your vision is impaired, and ultimately you end up being blind. And the eye on the bottom left is an eye that has a rating of 4. The images on the right are images processed by a convolutional neural network. So that's the technique that won the diabetic retinopathy competition. Now, just give you a sense for the results. The winning algorithm. So the way we measured the results of this competition was each eye in the competition had been analyzed by 2 ophthalmologists, and so the objective was to match the average rating of 2 ophthalmologists. And so if you can, and so the winning algorithm ended up, the discrepancy between 2 ophthalmologists was about the same as the winning algorithm with either ophthalmologist. So that's sort of a theoretical maximum. In this case, we don't have a sort of the ground truth is an ophthalmologist diagnosis. And so what we're trying to do is we're trying to match the diagnosis of an ophthalmologist. Now, so that was the best possible result we could have possibly hoped for this particular algorithm. Now, this is an important one because diabetic retinopathy typically impacts low-income populations. Seeing an ophthalmologist, there aren't, as I understand it, there's a shortage of ophthalmologists, and so it's quite expensive. Yeah, the most expensive part about being diagnosed for diabetic retinopathy is having a diagnosis by an ophthalmologist. So eventually, once an algorithm can at least triage some of the easier cases, should bring down the cost of diagnosis pretty dramatically. The next step with this algorithm is it'll be implemented, I think, alongside the fundus cameras, which take the images, and at first it will be used to tell the operator taking the photo that the photo needs to be retaken. So it hasn't received any regulatory approval, so it can't be used for actual diagnosis. But it can be used to say, if the machine can't make a diagnosis, then the image probably isn't clear enough and should be retaken. But eventually, it will go through peer review study, and then eventually an FDA type approval process. So still a long road to go. The proof of concept algorithm has been generated. It still has a long way to go before this is something that's being used in sort of a day-to-day type environment. The second medical use case, and I think this had involvement from the NIH as well as the Mayo Clinic and the University of Pennsylvania Medical Center, was to take EEG signals and predict seizures an hour before they happen. And we started off with dogs, and then I believe moved to humans. So we've done two of these competitions. And I believe that we started with dogs because it was easier to get a large enough training data set, because epileptic dogs, as I understand it, have more seizures than humans. Now, this was also a very strong result. The winning algorithm was able to predict a seizure an hour before it happened in 80% of cases. And so that's quite powerful for a few reasons. Firstly, there's a lot of research around, can you, I'm not going to pronounce the expression properly, but can you give a treatment that sort of counteracts the stimulus that one gets when they're about to have an epileptic fit? So there's sort of an active. So if you know somebody's going to have an attack, then there might be drugs or treatments that can counteract that or minimize the impact. And then, of course, there's the obvious one. If you can predict before a seizure is going to happen, activities like driving and other such activities, one can know that they can't drive, for instance, in the next hour. So that's this particular example. Again, this was won by a branch of deep learning called recurrent neural networks, which do very well on so convolutional neural networks do very well on image-related problems. Recurrent neural networks do very well on data that has a time series or a sequence-based element to it. And those are the two branches. Deep learning is kind of an umbrella term, with convolutional neural networks and recurrent neural networks being two sub-branches. Another EEG use case was figuring out whether you could predict. This was with, I believe, a group out of the European Union, or connected with the European Union. So figuring out somebody's hand motions from EEG readings. So can you figure out whether somebody's grasping or lifting based on their brain waves or the patterns of their brain signals? Now, it turns out that again, it was possible to predict using recurrent neural networks with about 98% accuracy whether somebody was grasping or lifting. Now, the utility of this is if somebody can think, they could operate a prosthetic just by thinking. However, obviously, the difference between grasping and lifting is pretty significant. These are not, one would need to be able to pick up much more subtle gestures in order to be able to have an algorithm that actually could direct a prosthetic, but this is a very promising first step. And so with that, I'm going to end my part of the talk. I might pause just for any questions, and then I'm going to pass over to Dr. Arai, who's going to talk about the competition that we ran with his group. So any questions before I pass over to Dr. Arai? So there's a text question. There are a couple of questions. So the first question is, what kind of predictive technology is Kaggle itself using to improve the website or other potential services in the future? We use a little bit, but not that much. So the way to think about us is we're more of a thin layer between, we're a marketplace, right? We're a thin layer between companies that want to get problems solved and data scientists who want to solve those problems. So we have quite sophisticated algorithms that we use to detect cheating. So sometimes what people will do is we make it very difficult for people to cheat. But one way that people try and cheat is they'll try and sign up for more than one account, because each account can only make 5 submissions every day. But if you have 2 accounts, you can sign up. You can have 10 submissions every day, and so people will often try and find ways of signing up for multiple accounts. Like a lot of people starting out attacking problems like this, we started out with basic heuristics, things like, if somebody uploads a submission without ever downloading the data, well, that's not really possible, right? So that's sort of a clear sign that somebody has multiple accounts. And we've moved on to more sophisticated machine learning methods, and we actually don't talk much about the methods we use for obvious reasons. The more we talk about them, the more people might figure out ways to try and game them. So once a competition is ended, what are the provisions for sharing the underlying algorithms and or code that contestants have used? So at the end of a competition, the company or the organization that hosts the competition receives 3 things. They receive code. It's typically written in Python or R. The vast majority of people on Kaggle are using technologies like Python and R. So they get code, documentation. So documentation should run through the things they tried that did work, that didn't work, what ultimately ended up working, as well as explaining their model. And then a couple of weeks after having the code and the documentation transferred, we do a screen share presentation with the winners. And the reason we do that a couple of weeks after the code and the documentation are transferred is because it gives data scientists, it gives the investigator or the researcher or the company the chance to have looked at the algorithm and have formulated questions that they need answered. So that's why we typically try and stagger it. But we do have a knowledge transfer process that is as I described. There's a question. What is the general format for the competition? Is there a training set, then an outer sample test set, yeah. So the answer is, what's the format for the competition? It's as I went through at the very beginning of the talk. So we have a training data set, and then we have 2 test data sets. One test data set where we give people live feedback on how they're performing in real time, and then a second test data set where to make sure people haven't overfit against the first test data set. And so then there's a question saying, could you imagine tilting those provisions towards more sharing in the community? There's actually already a lot of sharing, more than I have really represented in the talk so far. We have very, very active forums. In fact, I can I'll go to the competition that Dr. Arai is about to talk about, just to give you a sense for the nature of the conversation that happens during a competition, although my internet seems to be a little bit slow. I guess, here we go. So this is the competition to take MRIs and diagnose and measure ejection fraction. We have forums where people discuss different methods, different techniques, what they've tried that hasn't worked. What we typically find is that people are sharing learnings, but those who are winning rarely share their secret sauce. So there's we think that this strikes a good balance between collaboration and competition. And also often people will share things like, sometimes there's code required to, clean up the data, for instance, and often people will share things like the data cleaning code. That's not the thing that wins you a competition, but it's redundancy if every single person is doing the same thing. And then at the end of the competition, you can probably see so Tensia was one of the winners. She has put a summary of her method, so if the competition host permits it, often there'll be, at the end of the competition, a summary of methods, which is very, very interesting for data scientists who didn't win, because they get a sense for what they didn't do that might have made them successful. Any last questions before I pass over? Okay, I'm going to pass over to Dr. Arai.
Well, thank you, Anthony. That was a very nice summary of what Kaggle's all about. And I didn't know what to expect since I hadn't been involved with one of these big data competitions. But the basic idea for the 2016 Data Science Bowl was that the participants needed to create an algorithm to automatically measure the volume and ejection fraction of the left ventricle of the heart. The left ventricle is the main pumping chamber of the heart that pumps blood out to the body under high pressure so it can get everywhere around the body and has enough momentum to make it back into the heart. So not surprisingly, if the left ventricle is damaged, picking up a little bit of noise if someone has their speaker on perhaps. But if the left ventricle gets damaged, it can severely affect the patient and they can develop heart failure, a condition where a patient just can't do some activities or many activities of daily life. It also, when heart function becomes abnormal, not surprisingly, patients don't do well. A patient who survives a heart attack these days, most heart attacks are small and maybe has a 98 or 97% chance of being alive 1 year later. But if they have a heart attack that's complicated by severely damaged heart function, their chance of dying that year might be 5 or 8 times higher. So the bottom line is heart function is important. To do this competition, about 1,000 cardiac MRI scans from the National Institutes of Health and Children's National Medical Center were assembled into an anonymized competition pool, and Kaggle separated that into the essentially the learning cases and the final test cases. The competition was sponsored by Booz Allen Hamilton and Kaggle, and in the end, about 192 teams competed in this, at least by submitting a final submission. Can we go to the next slide? So hopefully this starts playing more quickly. On my screen, it still looks a little glitchy, but the images at the left side of the screen are a normal heart, and I've labeled on them the 4 heart chambers. This is probably the easiest view of the cardiac MRI scan for people to look at and think about. There are 4 heart chambers. The blood comes through veins into the right atrium, labeled RA. Then it goes into the right ventricle, RV on this diagram, which pumps the blood out to the lungs. Then the blood picks up oxygen and gets rid of carbon dioxide. It returns from the lungs into the left atrium, or LA, and finally goes into the left ventricle, which is the main pumping chamber of the heart for the rest of the body. And you can see the walls of the left ventricle are thicker, dark gray. And if you look at that movie, which is much glitchier than it would be on a diagnostic screen, the blood inside, which is the brighter gray, clearly the majority of the blood is getting ejected with each heartbeat. For comparison, at the on the right-hand images, we focus just on the left ventricle. The red arrows point to a part of the heart that has been damaged by a heart attack, and that section of the heart doesn't get smaller when the rest of the heart is trying to contract. And this is a relatively small amount of damage. If we go to the next slide and focus, the images at left are the same as I showed you on the first slide, but the images at the on the right side are from a patient that has a different type of heart failure. This is called a non-ischemic heart failure or cardiomyopathy. The left ventricular function is severely decreased, and it's also diffusely. Unlike the heart attack, which affected one particular part of the heart, this heart is abnormal basically everywhere in the left ventricle. Let's move on to the next slide. So when we try to measure the ejection fraction, we're essentially trying to see how big the how much blood is in the heart when it's full, and then how much is left after it's ejected the blood to the body. So the difference, how much got ejected divided by how much started in the heart, is the ejection fraction. And one of the reasons we were interested in this competition is that all the published literature has basically used hand-drawn contours on the heart to delineate where the blood is and how much blood there is. And it takes my cardiologists that are here for advanced cardiac imaging training about 20 minutes to make these measurements at the research level. And we do all our measurements at research levels. So that's a very time-consuming process. And the idea that a computer might be able to do as well as our cardiologists was an intriguing concept. And so if I'll go ahead and just jump to the first results slide here. This is the winning team, Team 1, versus the human measurements. And the left-hand panel shows the correlation of predicted volume on the y-axis versus the true volume. At least that's the volume measured by my fellows. And what you see is actually quite a good correlation. The R squared is 0.973, the slope 0.97, and the offset is relatively small, 3 mLs when you consider normal volumes about 100 to or so mLs of blood. And the blue dots represent the end systolic volumes, the red dots the end diastolic volumes, so that's why the red dots are all shifted to higher volumes, and that, as we would expect. The right-hand graph shows the ejection fraction, again, predicted ejection fraction on the y-axis and true ejection fraction on the x-axis. This correlation is not quite as good as the volumes themselves. The R squared's 0.772, but it's still quite respectable. And I think if we jump to the next slide, we have another way of looking at these same kind of data. In medicine, you don't always have well-distributed data over the range of measurements. And in that case, correlation statistics sometimes underestimate the how well those measurements are made. So there's a technique called Bland-Altman limits of agreement, which basically I have plotted here. So the y-axis on the left-hand graph is the difference between the predicted and the test or the test value or the cardiologist drawing, and the x-axis is the mean of the two measurements. And so in an ideal situation, there'd be no difference between the measurements, so the y-axis value should be 0 for any of the volumes that are average of the two measurements. Obviously, there's some scatter here, and you can measure the scatter, and usually we take the 95th percent confidence levels, or 1.96 times the standard deviation. And so the computer in this case was within 21.8 ml of getting the, for the 2 standard deviation limit. And for the ejection fraction, the limits of agreement range from 0.89 to 9.3. There's another measurement off here, and that's the bias. So if the computer systematically overestimated, the bias would be a positive number, whereas if it underestimated, it would be a negative number. For a bias of 0.613, considering our range, again, typical normals of about 100, it's a very small systematic error, and it's mostly random error that we see for the volumes. Same thing for the ejection fraction. It's a little bit larger bias, but it's still quite small. And to put this in perspective, if we go to the next slide, this kind of research was an important topic between about 2000 and 2003 when the field was developing and trying to prove its value. And if you focus on the heart failure data that I circled with the red box, the Bland-Altman limits of agreement for end diastolic volumes, you can see that the agreement between two humans making these kinds of measurements range from minus 18.9 to plus 28.9%. So clearly they had a bias of about 9 ml difference between the two investigators, and a spread that's very comparable in size to the results of the Kaggle competition. If you look at the ejection fraction data, it was a little bit better by human drawings, range from minus 6.4 to 6.7. So overall, I thought the results were very impressive for the Kaggle competition. Let's go to the next slide. Now, one of my fears when we started setting this project up was how good are my fellows' measurements? And I was afraid that, particularly since they're measurements by several different people as opposed to all one person, that there might be more random error in our data than there is in the published literature. So we looked at how well the different teams correlated against each other, and you've got plots here of Team 1's computer solution versus Team 2. And the correlation here is slightly better than versus humans, but not a lot better. And similarly for the ejection fraction, it's slightly better agreement between the two computers, but not dramatically better than what the human measurements compared. But nonetheless, very impressive results. Let's go to the next slide. These are the Bland-Altman limits of agreement. These, for the left-hand graph, the LV volume limits of agreement are definitely better than the human measurements. And the Bland-Altman, for the right-hand graph, the limits of agreement for ejection fraction are slightly worse than the published human literature. If we go to the next slide, Anthony, so I guess this summarizes basically what we saw. There's one more interesting slide after this. I probably should have changed the order. But the, you know, I thought the fact that, or considering that there was no clinical feedback other than a number of how, overall, how good their solution in the first 400 test cases or learning cases, it's pretty impressive that the competitors could hone in on any kind of solution. I've already said the comparison of automatic versus human is almost as good as the published literature for LV volumes, and the EF results are slightly worse. The fact that Team 1 versus Team 2 comparisons are better than either team versus humans might mean that the solutions just use very similar methodologies. But the other side of it is, as I already said, that human measurements are considered the reference standard, but they're definitely not perfect. And overall, these results clearly look worth pursuing to improve the accuracy, reproducibility, and speed with which the measurements are made. I mentioned our fellows take about 20 minutes to make the measurements and record them. Most of the computer algorithms did it in about 3 to 5 seconds, which included loading all the images and analyzing them and pumping out a result. Let's go to one last slide. Anthony put this together. So this is a graphical table plotting the cross-correlation between the various team results. You can see the color scale runs from blue, which would, I assume, be a negative correlation, or poor or no correlation. White's pretty much in the middle of correlation, about 0.5, and red gets up to a perfect correlation. If you look at the y-axis is one team and the x-axis is another team, we don't cross-correlate each team against itself. So the top red box is team 1 versus team 2, which you've already seen the results. You can see that the correlation with teams 3 and 4 not quite as good as against team 2. Team 5 doesn't correlate very well against any of the teams. You can see as a row and a column, and yet they had metrics that had good results. And so there's certain patterns in the way these cross correlations that suggest there are some teams that probably use similar methods and come up with relatively similar results, and there are a few teams that had probably moderately different approaches and don't necessarily correlate as closely with all sets of teams, but may correlate pretty well against each other. And we're now working with a few of the teams to try to follow up on these results and try to see if these teams are interested in taking it to the next step. We're pretty sure already we have enough data to publish something in the medical literature, but what we really hope for is to be able to take these algorithms and make for a usable solution that might be useful to diagnostic imaging. And with that, we'll stop on the last slide so you have contact information for Anthony and myself, and see if there are any questions.
I actually had a question. I don't know if it's against the rules, but for me to ask one. But I was curious. You spoke a lot about the machine versus human comparisons. I was wondering how much work had been done historically on trying to get a machine to measure ejection fraction, and if you could talk about these results versus anything that might have been done previously using machines.
Yeah, there are a handful of projects that have done that kind of study. I don't know the literature as well as I probably should, but none of those solutions have really had high impact in medicine. Most of them basically give a starting point, and so a few of these things have made it into products, and they give a starting point that the physician can then modify to make corrections. But none of them have I ever seen a solution quite as good as this. And most of them have also only been validated on relatively small data sets. With the exception, there's a project in New Zealand that has a fairly large number of patients that have been quantified by their method and by human comparisons, and their results look quite good also.
Okay, are there any other questions?
I have a question for Anthony.
Sure.
Go ahead.
What is the status of the $3 million Heritage Health Prize 2 competition?
So the Heritage Health Prize, just for background for others, was a competition to take historical medical claims and try and predict who would go to hospital over the next year. And that was sponsored by an HMO in Southern California called the Heritage Provider Network. They were interested, so one of the problems we had with that competition was the data had to be very, very, very heavily anonymized in order to make it public for obvious reasons. And so there was some interest from the Heritage Provider Network in the idea of running a follow-up with a subset of participants who had done well in the first prize, but on the non-anonymized data set. I believe the issues they have struck have been legal issues, so it's not easy to be able to release So it's certainly not worth doing a follow-up on heavily anonymized data. The follow-up would have been on non-anonymized data, but with a subset of the community. And I think even that we've had trouble, or they've had trouble, I should say, getting the ability to release that data set. So this is why, just more generally, medical EMR data and claims data. So they were basing their competition on claims data. EMR data and claims data is very difficult, just because it's so personally identifiable. And so one of the nice things about medical imaging, ECGs, EEGs, those sort of more diagnostic-oriented competitions is they're much easier to strip out the personally identifiable characteristics of them. You don't face those sort of issues.
So there are a couple of questions on the chat to Andrew. The first one is, have the teams shared their solutions? And the second one is, has NHLBI done any other data science competitions?
The first question's easier. I don't think NHLBI has done prior competitions, but I just recently learned that they now have a new grant mechanism to be able to do a prize, and so that may be something that happens in the future. In terms of the solutions, one of the rules of the competition was that they had to submit their code, and that it is available. I don't know if all of the code is submitted, but I know certainly know that leading teams have got it in.
And just a follow-up to that. So the way it works is we typically give prize money to the top 3 to 5, and the top 3 to 5 are obliged to provide code, documentation, and typically a screen share. So so not everybody, I think in this competition, I think we had 750 teams participate in stage 1 and 192 participate in stage 2. Not all 192 are obliged to submit their code. It's only the top performers who win prize money.
So following up on that, though, have you ever run a competition where the prize was something other than money? Because I know, for example, NCI has done this where a competition where the prize was a paper in a prestigious journal. Is that something that Kaggle does?
We have, Kaggle has a limited ability to do, I guess, pro bono type competitions each year, and there's some appetite for it. So if the way we judge as to what we will do pro bono, both in terms of our fees, but also in terms of prize money, is it has to be something that is new and novel, that hasn't been done before. And the reason we take that approach is because it's not going to, the community will get very excited about an application that's different to anything they've seen before. And so even without prize, you'll get participation. But what we don't want to do, our reputation is very important to us, and we don't want to host a competition that is unsuccessful. And so we don't think a competition is going to attract a critical mass of entrants because it's not interesting or novel enough without the sort of extra lure of the prize, then both for competition host's sake and for our own reputation, we typically will steer away. So it's more on a case-by-case basis that we can look at it.
Okay. Anthony, there is another question for you on the chat, and it's asking if you can comment on which problems and which types of data sets are good for these competitions. I know you talked a little bit about that in the beginning, but if you could say a little bit more, that would be helpful to us, because at NIH we think a lot about what's the best mechanism to solve each type of problem?
Yeah, so Kaggle is good for not all data science machine learning problems, but a decent proportion. First of all, the data has to be released publicly. Like with any machine learning problem, there has to be a decent volume of it. So I think this one was this competition was probably towards the lower end. It was 1,000 MRI images. So it's on the lower end. I think 500 would be probably an absolute floor. The question has to be very well specified. So what you're trying to answer has to be so well specified that we can distill it into sort of a ground truth type measurement, whether it be a diagnosis or something else. So those are typically the characteristics. Where Kaggle tends to do better is if the data set is relatively simple, the degrees of freedom for the community are not that, there's not that many things they can do that a researcher couldn't do themselves. The more complex the problem is, the richer it is, the more combinations of things that the community could try, the better the larger the difference between what the community can do and what an individual can do. And so a lot of these problems, the ones I highlighted, like with medical images, with EEGs, with ECGs, with those sort of problems tend to be much more difficult, and that's where the community typically really, really shines.
So thank you. I mean, it's 2 o'clock now, so I think we need to end. But on behalf of NIH, I want to really thank you, Anthony, and Dr. Rai. Thank you for joining us as well and telling us about the particular competition that NHLBI ran. And also, thanks for putting your contact information up there, because I think there will be a lot of interest from across NIH on this very novel platform for getting to and reaching the machine learning community. So thank you very much.
Yep.